it fits inside an integer, an unsigned integer, and even. Or it's not a perfect square and less than 256. Okay? Okay, we're back. Search special. Okay. So this is a function, takes x, and we're going to say, so x is a field, a finite field. Think about this, it's like a number, it's very big, it's like a big number. So it's bigger than 32 bits. But what we can do is we can say field 2 bits on it, which is a function that's in our standard library. Give it a length, 32, and then we get back the bits of the, so like 0, 1, 1, 0, 0, 1, 1, 1. Yes. And then let's check if it fits in 8 bits. Let's see. Okay. This is ad hoc. I did not plan to do this, so we'll figure it out together.
Maybe get there some substring and and then make it to the list.
Yes, thank you. Yes, get the bits from 8 to 24. No, start at 24 and get 8. Yeah, that's 32, right? Okay. It's an array converted to a list. If any of the bools, if any of them are 1, it's a bool list. So true is 1, false is 0. Negate it. And so if any of them are 1, yes, then this is true. When we negate it, it's false, which means it doesn't fit in 8 bits. Okay. Is it a square? There's a primitive operation in SNARKs. So this is just given to you. And then we do an assertion. So we're asserting that either one of these is true. So the first one, a perfect square and less than 232. An even is square. And look at the top bit, the last bit, I should say. And then the second thing, not a perfect square and less than 256. Not is square, fits in 8 bits. Make sense, little? So it's pretty, looks like normal code. And then we take this function and we can pass it into this special run main. We give it the input, like the type of the input that we described over here. Cool. Witness and name, and then we get a snark. Cool. So this is like a toy example. Now I'll show you proof of stake code inside of CODA, inside of SNARK. Okay? This is more complicated. You click the other tab.
Careful.
This. Okay. So leave it where it's scrolled. Yeah. Okay. So it's a big file. Okay. This is inside CODA. Source lib consensus proof of stake. So Ouroboros. So it's a very big file, but if we look at, let's start here. Okay. Yes. So the type of the SNARK variable inside the SNARK circuit. This is, sorry, very dense, but a length, VRF output, an amount, a slot number, epoch information, a bool, and it's substituting that into polygon. Here. So length, epoch. Yeah, this is the state for proof of stake. anyway, not important. By the way, this is version 1, so it's OCaml with monads. So let's go. Okay, this is what I want to do. The update function. So we had old consensus state. We have a transition to new consensus state. We had an old state hash. Think of it like the last tip of the blockchain. There's a supply increase. So if there's a block reward and we're minting new tokens, think of this as the top of the ledger, the Merkle root of the ledger, and then the VRF, verifiable random function. It's remember I was saying you throw a dart in proof of stake. The network decides who gets to throw the dart with the VRFs. So it's like a random number generation that's secure. Okay, so this is a function. It takes these parameters. And now we're in monad worlds. Here we are. Okay, so let's start here. So all these functions are defined above in this file. We're on line 1925. So you can read at your pleasure. Yeah. Slot. So Ouroboros breaks time into slots and epochs. From just the slot, we can compute where we are in epochs. It's like if we say like the current time now in seconds, like a UTC time, we can take that number and figure out what day of the week it is, the month, the year, stuff like that. So we're getting the epoch out of the consensus state, and in here we're not doing any SNARK assertions. So you can tell if it's doing assertions or not if we are in the monad. I'll show you an example of that in a minute. Sorry. This is the update function out of the SNARK. Sorry about that. Let me go a little faster. We're saying figure out the new total currency. Well, you look at the previous total currency, the supply increase, you add it together, and you make sure that the transition is either equal to the genesis transition or the transition is greater than the current slot. And then you update some information about ledgers and do some other stuff with consensus, and you get a new state. Okay, so let's look at the version inside the SNARK. All right, let percent snarky_def. Now we're in the SNARK. Same parameters, but this time the variables, SNARK variables. So previous state, transition data, previous protocol state hash, the last block, the new supply, and and the ledger. So, okay. We're in the SNARK. So previous state, we get out the local slot. Okay, let percent bind. The bind means we're doing assertions inside the SNARK. So here we're checking that this is less than that, and we get back a Boolean. But if this less than operation has some sort of overflow bounds, I don't recall off the top of my head, but we could scroll up and find it. Then this could be this could fail the proof. But it also gives us back a value. So like we can define functions that are in the SNARK where we get back values, but we also are writing down assertions. We're adding predicates that there exists such that so and so and so. This is one of the such that's potentially with the bind. Okay. Too fast. All right. Okay, in here is Genesis. We have a function, and then we're saying, okay, if either this or this is true, then the assertion passes. If one of them is false, then here we fail. And when we're trying to, if we're calling update var, if we're creating a snark with this, the snark creation will fail here. If this predicate fails. So yeah, more just moving stuff around. This is interesting. There's an if statement here. So because we're inside of a snark, there's no if. You build snark programs as an arithmetic circuit. So what that means is essentially you just have numbers that you can multiply and add, inverse, things like that. There's no branches, but you can simulate a branch. You can simulate a branch by multiplying by a number that's either 0 or 1. So I wish I had a whiteboard, but you know, so let's say you have your 0 or 1 in like b, variable b. You can say b times the true condition plus 1 minus b times the false condition. So if b is true, if it's 1, then b times true condition, you get true, plus 1 minus 1 is 0 times the false condition, you just get true. And if b is false, if it's 0, 0 times the true condition, you get 0, 1 minus 0 is 1, and 1 times the false condition, you get the false condition. So that's essentially what the if does. So it's a function that takes a bool, the true case, and the false case. So the nice thing about Snarky is we can decompose our logic into functions so that we don't have to deconstruct the raw equation to understand that it's an if condition. We just know that it's if because we can name it if, which is nice. Then we check our VRF, and VRF check is a function inside the snark that we defined earlier in this file. There's this interesting thing that there's a cryptography vulnerability if you don't randomly shift your point on the elliptic curve. I'm not so familiar with it, but I'm sure some of you cryptography masters know about this. We have to make sure it's not 0. So by shifting it by a random amount, the probability that it's 0 is astronomically low. Okay. Here's the add, the previous total currency with the supply increase. And this is a checked add. So if this add overflows, then the assertion fails. So we make sure that the amount, in this case, amount is a 64-bit integer. So if this add does not fit in 64 bits, then the snark will fail. Cool. Some more stuff. Next epoch data. This is interesting. So here we're computing a large record. So we make the seed, etc. There's some ifs. Yes. None of this is different. Cool. Okay. And then we return a success boolean if our VRF is satisfied and the new state inside the snark. And then what we can do is we can run, the thing outside the snark and the thing inside the snark, and we want to make sure we get the same information. And there's some code. I don't know. We use GraphQL in our protocol. It's interesting. Yes. I don't know. We can find more interesting parts of this code if people are interested. Otherwise, we can talk about something else. Are there any questions? We didn't give time for questions before, and maybe we can have a translator if you prefer to speak Korean. But any questions about anything? Yes.
How about storing state?
storing state. How do you do that? In CODA or in a SNARK? In the SNARK. So there is no state in the SNARK. It's like a pure function. So but you can sort of simulate state by just making it an input to the proof function, and then you feed it like let's call it like state 0, and then you do something and you can run your SNARK and you get and in SNARK you can also produce new values, so you can produce your state 1, and then the next time you call the SNARK you give it state 1. So you make all of your state into parameters to the function, if that makes sense. Cool. More questions about CODA, about SNARKs?
Is there any trade-off for CODA to use recursive SNARK compared to other SNARK?
Yeah. Yes. So CODA uses recursive SNARKs, which I didn't talk about much in the talk. I guess the picture inside a picture bit. For the blockchain, well, okay, we use recursive SNARKs in 2 places. With transactions, it's more like you saw in the presentation, where we sort of we start with a bunch of individual transaction proofs, and then we group them together in pairs to the top. And then we take that top proof about all the transactions in a block, and we put it inside of the blockchain proof, part of which is running this consensus code that we ran before. And then that is recursion in the sort of linear sense, like a list. So we just get a previous proof from the Genesis block to now, and then we get one more block. And then we combine those, and we now have a proof from Genesis to the new block. Okay. So now there's some background, and now I can answer your question. Are there trade-offs to using the recursive SNARK? Well, doing the recursion is a little slow. So in order to do recursive SNARKs, you have to implement SNARK verification inside of the SNARK code. And SNARK verification is fast. It takes on the order of 100 milliseconds, maybe less on a very fast computer. On a CPU, on a Turing machine, on a x86 processor, if you convert that logic into a SNARK circuit, it's slower. So you measure performance of SNARK programs by the number of constraints. Premiere, 30 minutes. And the number of constraints for a multiply is 1. The number of constraints for an add is 0. So you can essentially add numbers for free in a SNARK. Multiplication costs 1. SNARK verification, recursive SNARKs, is in like the hundreds of thousands of constraints, and it's at least 100,000. I think it's more than 100,000. And the total amount of constraints that we have in all of CODA is something like it's under 1 million. So more than 10% is the recursive. I don't remember off the top of my head how much. It could be as much as half or so. And we have a lot of SNARK code. And it's very, very optimized. Like every circuit is hand optimized to minimize constraints. The trade-off, I would say, well, there's an interesting. Someone can stop me if I'm just going on and on. I'm just going to keep talking about things I find interesting. You tell me if it's boring. Okay. So there's an interesting question of when do you do the recursion? Because you can say, instead of doing like 1 block, maybe you can create 5 blocks and write a SNARK that checks a proof and then adds 5 more blocks, and then that creates a new SNARK that then you do recursion on. Yes, or I guess it's better to say that the transactions where we're pairing them up. Maybe we want to pair up 3 at a time instead of 2. turns out the optimal number is E. So 2.72 is the right amount. I don't remember why. It's just interesting. E is an interesting number, but I don't know. It's hard to say. It's a hard question to answer. What trade-off against what?
I mean, as you said, the proving time.
Proving time, yeah.
Let's see, slow. I want to know that
How much slower?
usually take to.
Yeah. Well, I can give you specific performance numbers for CODA, but I don't know off the top of my head like what % of that is the recursion. But so we have we use a Groth16-SNARK. There's lots of different SNARK backends. We're working on a new backend now, but in the Groth16 backend, which we're using the libsnark library, which is optimized for concurrent native code on a CPU. So it uses vector adds, SIMD, and multithreading. It takes around 1.5 minutes on a MacBook Pro to produce block in our network. And it is directly proportional to the number of constraints. And I think we have like 700,000, 800,000, something like that. So 800,000 constraints takes about 1.5 minutes. We're working on a GPU implementation. We ran a challenge for folks to make a GPU version, and we have the person who won that challenge, we're contracting with them to build out a production version. We've already seen an 8x. No, I'm not sure. We've seen more than a 4x improvement already. So it's something, I don't know, that gets us under 30 seconds. But the different SNARK backends have different performance characteristics. So one of the other performance trade-offs that you make is the size of the field, size of the finite field. So in the version of CODA that's running now, we use a 763-bit prime number that we do our finite field over. So it's like, that's very large. And we need that for security reasons. But with the new SNARK backend, which is a variant of Halo, if you want to Google that, anyone, we can safely reduce the field size to 380 bits around. And that has a quadratic speed up, which is nice. So that's like a 4x speed up by having the bits. But then there's also more performance, negative performance, performance losses from switching to the new backend. So there's lots of parameters between. Long answer, but hopefully somewhat interesting for some people. I'll just keep standing here. You can keep asking questions. Also, feel free, if you don't want to ask in front of everyone, you can come up to me. I'll be here, and I'm happy to answer any questions. Very technical, very non-technical, whatever. I can do anything. Well, okay, there's only so deep. I'm not a cryptographer, so some cryptography questions I might not be able to answer, but I know how the code works. So, any other questions that anyone wants to ask in the group? Okay. Cool. So yeah, please come and talk to me, and we can find a translator if you want to speak Korean. I'd love to talk to you. All right.
네, 혹시 질문 있으신데 통역이 필요하신 분 계신가요? 네, 없으시면은 저희 고생한 브랜든에게 박수 한번 부탁드리겠습니다.
Also, I can show some. If anyone wants to see anything in particular, I can talk about it.